12 is about mechanical waves and sound. These are not a particularly difficult chapter, but it is a really lengthy chapter. A lot of books might have divided this material into 2 parts, so there'll probably be several videos to get everything in. But we're going to start with talking about mechanical waves. A mechanical wave requires a medium to travel through. A medium is just some type of material. It can travel through a rope, it can travel through water or air, it can travel through a steel rod, but it has to travel through matter. Later in the spring, we'll talk about electromagnetic waves. Those are things like light and radio waves. Electromagnetic waves can travel through a medium, but they don't need one. They will travel through a vacuum. But for right now, we're going to look at mechanical waves. The mechanical wave you probably picture is a transverse wave. In a transverse wave, the particles oscillate or vibrate perpendicular to the direction of wave travel. If I were to draw a picture of a transverse wave, this would be an equilibrium line. And a wave looks like this. It looks like that classic sinusoidal wave that you think of when you think of a wave. Let's assume that this wave has a velocity and is traveling this direction. That's the direction that the wave is transferring energy. Waves transfer energy from one location to another, but they don't transfer matter. That's different than a particle method of energy transfer. Particle method of energy transfer would be like picking up a baseball and throwing it through the dining room window. I transferred energy to the dining window, but I also transferred matter. With waves, the matter vibrates and oscillates, but it actually always stays close to its equilibrium position. If we were to draw this wave at a different time, it might look like this. Now, you may think that that matter actually changed location, but it didn't, because this piece of matter right here is that same piece right there, or anywhere where I pick. That's the same dot right there. What's happening, and I could possibly extend this wave back a little bit. Extend that back. Is that any particular point on this wave is oscillating, in this case, up and down, perpendicular. This point right here is moving from here to here, down to here, back up to here. It's vibrating back and forth right here. This particular one is vibrating back and forth from here to here. Any point we pick, the actual molecules or the particles that make up that rope or that water, whatever the medium is, the molecules or the particles are vibrating up and down, but the wave is transferring this way. So wave, the particles vibrate about an equilibrium position. In this case, this dotted line represents an equilibrium line. Now, there are other waves called longitudinal waves. Where they oscillate or vibrate parallel. That's a little bit harder to draw But I can draw it pretty well if we look at possibly sending a pulse through a slinky, not shaking the slinky up and down, but sending it through. If I send a pulse through a slinky, I'll have places where the springs are pretty far apart, and then I'll have places where they're bunched together in a pulse. So you can see these pulses. These coils on my slinky are vibrating back and forth in this direction. Pick any coil, doesn't matter which one. It's vibrating back and forth about its equilibrium or rest position. Longitudinal waves are actually pretty common, but they're not as visible. Anytime you have a wave that's traveling through a fluid, that can be a gas, like the atmosphere, or it can be like water underneath the surface, waves travel as longitudinal waves. There is a third type of wave called a surface wave. A surface wave on the surface of a liquid, like water, has characteristics of both longitudinal and transverse. So those water molecules on the surface move up and down and back and forth, and the result is they actually move in a circular pattern, which gives waves that kind of undulating appearance. They don't really look like a transverse wave if you look closely. But we're going to not really talk about surface waves other than to say that they do exist and that they have characteristics of transverse and longitudinal. Underneath the water or through the air in most liquids, we get longitudinal waves. If I were to think of this as a wave traveling through sound, we would have places where the molecules were fairly spread out, and then these concentrations where the air molecules got pushed together. And then here we've got a third place where we've got a concentration of molecules closer together and then in between, these kind of spaced out. Okay. Those are longitudinal waves. I think of them as being pulses going through in the same direction of the wave, but it's like you're vibrating back and forth like this. One of the things we'll talk about more, but I want to go ahead and mention, is how fast this wave travels depends on the medium it travels through. In particular, it depends on some of the mechanical characteristics. If it's traveling through a solid bar of metal, it would depend on what type of metal, and what the density of that metal is, and how close those molecules are together. If it's traveling through a gas, it's probably going to depend a lot on the temperature and pressure of the gas. If it travels through a rope or a string, it's going to depend on how much tension is in the string. What it doesn't depend on is the source of the sound. The source, or I said sound, the source of the wave. To start the wave, you need some type of source to cause this vibration. The source can determine the frequency of the wave. It can determine the amplitude of the wave. Those are the two things that the source can determine. How fast am I shaking that? How tall an amplitude if I'm thinking of shaking a slinky or a string? The source can determine frequency, amplitude, but how fast a wave will travel depends only on the medium. All right, there's a lot of vocabulary we want to look at. I'm going to use a transverse wave because it's easier to demonstrate, but the vocabulary is the same even if we're talking about a longitudinal wave, with the exception of two words. So let's draw a transverse wave. And I wish I had drawn the equilibrium line first, but I'll try to aim right to the middle. Not bad. We could also think about, go ahead and draw no, let's not do that. All right, high points. They're called crest. Low points, That's a trough. If I think of this as being an equilibrium position, all of these molecules are vibrating up and down, above and below equilibrium. We can assume the wave is traveling to the right. This distance from here to here, from equilibrium to its maximum displacement, is called the amplitude. The symbol for amplitude is a capital A. It is a type of distance, so our SI unit will be meters. And it's usually described as something like the absolute value of the maximum displacement from equilibrium. Even though I didn't draw a longitudinal wave, in a longitudinal wave, it also has an amplitude that is the maximum displacement from equilibrium. The only words that will be different is longitudinal waves don't have crest. They have areas of what you might call compression, where the coils are crowded up or the air molecules are crowded up. So if I were to draw instead a longitudinal wave, I would have to talk about compressions, where those coils were bunched up, and they have expansions, where those were spread out. So not exactly the same thing, not highs and lows, but places of high concentration of particles and areas of low concentration of particles. Our next word we want to talk about is wavelength. Now, the wavelength is represented with a symbol called a lambda. One of our Greek letters looks like an upside down Y. It is also literally a length, so we will measure that in meters. It is the shortest distance before the wave repeats. So what's that smallest pattern we can get before the wave repeats? It turns out we can measure it in several different ways. We can go crest to crest, or compression to compression. That will be a complete wavelength. If we start here at one crest, and we go over here to the next crest, you can see that after that point, we would repeat crest to crest again. So that would be a wavelength. We could start at a trough. We could go trough to trough. If I went trough to trough, from one trough over to the next trough, that would be one wavelength, because after that it repeats. Or a lot of times we might prefer to say, you know, let's go from equilibrium right here to a crest, back to equilibrium, down to here. That's also one complete pattern, one wavelength. If I had drawn this perfectly, all of those wavelengths would be identical. I didn't draw it perfectly, but you get the idea. So we can go crest to crest, we can go trough to trough, or we can go from equilibrium to crest, to equilibrium, to trough, back to equilibrium. And that will give us that one complete pattern. All right, I'm going to have to erase so I can keep my picture, but I'll give us a lot more vocabulary. There's a lot of words. The frequency means the same thing it meant in simple harmonic motion. It's simple as an F. The unit is hertz or per seconds, and it is simply the number of cycles per second. So nothing really new there. Angular frequency, omega, is simply 2 pi f. It's often written as either hertz or it may be written as radians per second. But a radian per second, again, is technically still a hertz. The period, that says capital T, the unit is the seconds, and it is the time for one cycle. In this case, one cycle would be the same as the time for one wavelength. That's a complete cycle of the wave. So frequency, angular frequency, period, they don't have any new meanings. So we already understand what those words are. We still have the relationship that the period is the reciprocal of the frequency and vice versa. So in terms of thinking of formulas, those look exactly the same. All right, this brings us to one of our important relationships. And that's the idea of wave speed. How fast does the wave travel? Well, wave speed, like any speed, should be calculated using distance over time. That's a chapter 2 definition of speed, distance over time. Our symbol for speed will still be a v. The distance that we know is a wavelength. That's an easily measurable distance. And the time it takes for one complete wave cycle or wavelength is the period. This gives us the formula V equals wavelength over period. It's a perfectly great formula. There's nothing wrong with it. However, if you remember that 1 over the period is the frequency, it can be rewritten as V equals wavelength times frequency. This is the way we see it written more often. That's probably the single biggest wave formula you need. Now, I want to be really careful here. You could make the mistake of saying, oh, it looks like the frequency determines the velocity. No, the medium determines the velocity. Or you might think, oh, it looks like the wavelength determines the velocity. The medium determines the velocity. However, for a particular frequency, it must have a certain wavelength, or a certain wavelength will have a particular frequency once this number is set. So if we are in a particular medium where we know this speed, wavelength and frequency will be inversely proportional to each other. In a particular medium, as you increase the frequency, that wavelength will get shorter. Wave speed will stay the same. Okay, so this is a really good equation in the sense that it relates wavelength, frequency, and wave speed. But I don't want you to think that how fast the source shakes somehow determines wave speed. It won't. That'll be determined by the medium. What tends to happen is the medium determines the wave speed. The source can determine the frequency. And then the wavelength is a result of those two items. Okay, let's keep moving. All right, I'm not going to draw a picture of a longitudinal wave, but there is one in the notes, so it's one in the book. All of the terminology is the same, so I don't think that's anything that we need to look at. All right, let's talk a little more about wave speed. We do have, for the most part, if you want to know the speed of a wave, you have to probably refer to some table. If you're using the 10th edition of the textbook, there's a table on page 359. If you're using the 11th edition, there's a table on page 363. That'll have all kinds of things like sound travels at 343 degrees at 20 degrees Celsius in one atmosphere, that type of number. Sound traveling through water is about 1,500 meters per second. However, we do have one formula we can use, and that is the formula that tells us the wave speed in a rope. And it says that the wave speed in a rope is given by the force of tension divided by mu. Now, this is the tension in the rope. Intuitively, it makes sense that the tauter the rope, the more tightly that rope is stretched, the faster that wave will travel. It goes with our intuition pretty well because those oscillations will be quick. The second one, well, let's write down that. That's the tension. And of course, it's a force, it's measured in newtons. This is the mass per unit length. And it's going to be in kilograms per meter. Again, if you have a heavier, thicker rope, we would expect that the wave would travel more slowly. Just think about how quick you think it would travel through something like a guitar string where it's very taut and very light compared to a big old heavy jump rope, which is harder to get taut and is certainly much heavier. So it's a pretty easy relationship. You might question, do the units make sense? And we can do a quick show on how the units work out here. I know that tension is in newtons, so we have the square root of newtons over kilograms per meter. A newton is a kilogram meter per second squared. This is a kilogram per meter. If we do, remember when you divide by fractions, you multiply by the reciprocal. So this is like kilogram meters over second squared times meters over kilogram. And it's the square root of that whole thing. You'll notice quickly the kilograms cancel. You're going to end up with meters squared over second squared. When you take the square root of that, you do get meters per second. You do get units for velocity. Sometimes it's just not obvious, but as long as you stick to the SI unit, I promise all of our formulas are right. Let's do an example. I'm going to leave both of our formulas up here in case we need either one. If we have a rope, the speed in that rope is the square root of tension over mu. Mu is one of the most overused Greek letters in physics. It represents lots of things. And we know that that wave speed then will cause this relationship lambda f. Our problem says that, I don't want to tell you the whole story, but basically we have a rope that is 80 meters long. At the end of the rope, we have a mass of 20 kilograms. The rope itself has a mass of 2 kilogram rope. So remember, the rope has mass also. The question wants to know how fast will a wave travel through this rope? Because there's a worker down here at the bottom of this mine shaft or whatever. he's going to thump the rope to try to send the signal back up to the top or something. How fast will it travel? First of all, what's the tension in the rope? Well, our free body diagram, let's go way back. Down here at the bottom says there's two forces. There's the weight of the box, and there's the tension in the rope. This is a static equilibrium. There's nothing moving. So I know the tension in the rope is just mg. So 20 kilograms, 9.8 meters per second squared. And the tension is 196 newtons. Okay, that's one thing we need for our formula. The mass per unit length is 2 kilograms divided by 80 meters. Comes out to be 0.025. We do have 3 significant digits, so I'm keeping that extra 0. There's our mass per unit length. So the wave speed, 196.0250, and it comes out to be about 88.5 meters per second. So that particular rope has this mass per unit length and this tension. I could make the wave travel faster if I added some more weight and made it more taut. It takes a lot of weight, but I could do it. But it's going to travel about 88.5 meters. So alright, now that we know how fast the wave will travel through this rope, what happens if we send a wave through it with a frequency of 20 hertz? So we send a wave, frequency of 20 hertz. Now I can use this formula. We put in the speed, which was determined by the medium. We put in the frequency, which was determined by the person down here that sent a pulse through it. And as a result, we get a wavelength that's about 4.43 meters. So it'd be fair to say the wavelength depends on wave speed and frequency, that combination. All right, this last part won't be hard, but it's mathy. Section 12.4 talks about a mathematical description to describe a wave. In other words, we want an equation that describes this wave. So let's picture a wave. There's my equilibrium line. Here's my wave. And like I said, I'm not guaranteeing that I'm drawing that perfect by any means. We know that all of the molecules are vibrating up and down. In fact, if we picked a different time, the wave might look like this. There's lots of different positions that wave will have. What it looks like depends on its initial conditions, and then what time are you talking about, and where on the wave are you talking about. We're going to let the wave, the solid line, the wave start right here. This is our position x equals 0 at t equals 0. So at the very beginning, we're going to say that that particular particle is at x equals 0 at time t equals 0. We can describe the vertical position of any point on this wave if we know two things. One, what's its horizontal position? Because right here, if you were at the point of maximum amplitude at t equals 0. You have that particular x value. Y does not equal 0. See here, y equals 0 when x equals 0 and t equals 0? But that's going to be different. So what we see is that displacement of those particles, that y value, depends on where you are along this, your x-coordinate, and it also depends on what time it is. So we get a function of x and t. That's a little different for most of us. So this is the vertical position, which describes the wave at any time. Y is a function of x and t, and it is equal to a sine 2 pi t over t minus x over lambda. We've already described all of these. This would be our amplitude. Hopefully it's going to be provided in meters. This is the period in seconds. This is the wavelength in meters. This will be at any time t in seconds. This will be at any time position x in meters. If we go to x equals 0, t equals 0, all of this is 0. Sine 0 is 0, so we're right here. If we pick a different position at t equals 0, let's pick a position of 1/4 lambda. Notice the wavelength is all the way to here. If I were to pick a position of 1/4 of a wavelength, and I put in 1/4 of a wavelength at t equals 0, this would simplify to 1/4. 2 pi, this will still be 0 because we're talking about t equals 0. 2 pi times 1/4 is just pi. What's sine pi? Oh, sine pi. Did I do that right? Oh, this is over 4. This will be 1/2 pi, pi over 2. What's sine of pi over 2? Sine of pi over 2 is 1, and it would give us that point. I don't want to pick a lot of points. I just want you to understand this formula really does work to describe the position of any point. Okay, let's just do one example. If my equation looks like this, let's answer some questions. What's the amplitude? The amplitude is 5 meters. What's the period? Well, look at this here. This is t. This is 1 over the period. So 1 over the period must equal 0.3. 1 over the period equals 0.3. Another name for 1 over the period is the frequency. I know the frequency is 0.3 hertz. That means if I take the reciprocal, the period is about 3.3 seconds. And finally, this last part here, if I look at this, 1 over lambda has to equal 2. If 1 over lambda equals 2, then lambda must equal 1/2 or 0.5 meters. So I would not expect you to be able to write this equation unless I said, oh, the amplitude is this number, the period is this, or the frequency, or the wavelength. And then I would think you could fill in those known values. Or if I give you the equation, you can pull out those known values. That's the most I would expect you to be able to do with that equation. Okay? All right, I'm going to stop here. We're going to pick up with more wave behavior in the next video.